I didn't do that.
Okay, well, let's see, anything more I should say about the test? Well, you need to review it yourself and see any mistakes you made and ask yourself, why did I have stuff written down on my summary sheet, for example, to help me out right or not? So whatever, so you can think about that in your own specific case. If you want to talk to me about any of the problems on the exam, see me outside of class, that would be just fine. Overall, the results were pretty good, so I'm encouraged about us proceeding along this semester.
So if we did bad, then you would stop and we would have went back over it?
Yes. So, okay, today I have a few mild things to continue on with for you. Actually, next week is the spring break, right?
Yes.
So I won't see you next week. We'll be partying it up, I guess. Is that what we're supposed to do on spring break?
Relaxing. We call it relaxing.
Relax? Oh, okay, that's a new take on it. Okay. But anyway, I wanted to make a few comments here at the beginning of class today about our textbook. I picked it up and started to read it here a week or so ago, and I was impressed again just how well done this textbook is. There's just a nice layout of the material, and I noticed also that it follows very nicely the notes that I've been giving you. It uses the same notation here in the textbook as you've seen in my notes, and that's good that we have this uniformity there that way. But I just wanted to call your attention to some of the stuff that's here in the textbook, because in a way you didn't really have to be reading this to be following along in the class. So our book begins in chapter 19, I believe. Where is it here? So this is the first chapter that we have, chapter 19 of the big book. Two-factor studies with equal sample sizes. So anyway, we had a separate handout about two-factor ANOVA problems, and this chapter complements that handout. It basically covers the same thing with a fair amount of detail along the way. So we have the notation of our two-factor model. Goes into the sums of squares, the expected mean squares. We see a table like this, which summarizes the sums of square formulas, the degrees of freedom, and the expected mean square column. Now in this chapter, the factors are fixed. So these are the results of expected mean squares when we have two fixed factors in the experiment. And those will agree with other things that we've seen on that issue as well. So test for interaction, test for the main effect on A, test for the main effect on B, somewhat repetitive because it's the same stuff, just switched to the other factor. Then he continues the example. And he talks about contrasts, where we want to put more than one mean together into our target parameter. Talks about multiple comparisons, Chaffee, Bonferroni, and somewhere in here is tricky for the pairwise case, I guess. So he's got some formulas and some examples of this kind of stuff. So this is the kind of stuff that we've talked about with our class handout. And I just wanted to quickly blow this by your eye to show you that it's stuff we've already talked about that you have here. Then there's this chapter 20, two-factor studies where you have one case per treatment. That means that in the layout of the data, in each cell you have one observation. One observation in each cell. If you have one observation in each cell, the problem that you encounter is that you don't have any sum of squares error. Sum of squares error is 0 officially, if you like it that way. And so something else has to be done in this case to get any kind of statistical testing done. And what's effectively going to be described here is that they're going to say, well, you assume a model. Let's see, where is it here? It'd be like this one here. So we have mu, alpha I for row effect, beta J for column effect. Notice there's no interaction here. And then there's an error term. So basically, the model assumes that all the interaction parameters are 0. And basically by doing that, it lets them calculate sum of squares interaction and use it as an error. So sum of squares interaction is going to be used as an error. And there's an ANOVA table here talking about the sums of squares. Notice that error is labeled, what the heck? Error is labeled AB. So the AB interaction is the error in this model. There's the usual formula for the AB interaction. And it's going to be used as the error in forming f-tests about factor A or about factor B. So it's kind of a simple idea, basically. Taking this model, assuming the interactions are 0, so we can use the interaction as an error and do some of the usual tests. So let's see, this goes along 21. How did I get into 21? Oh, there it is. So we talked about this before. We talked about two-factor studies even, and randomized complete block design. And if you look at the material that's here in the textbook on the RCD design, it should look very similar to our class handout. Same notation is used along the way. So one of the things that's going on in a randomized complete block design, let me look at this data example here on page 85 actually. We have a factor that we're interested in. Here it's the column factor. It has 3 levels in this example. And then the row is simply block. We're usually not interested in block, but we have blocks in the experiment for their purpose. So anyway, looking at this, we have 2 factors. We have a row factor and we have a column factor. And we have one observation in each cell. So we're back in the same case as the previous chapter. What are we going to do to make a test of a hypothesis about our main factor? Here it's the column factor. Well, we do the same thing as what was suggested in the previous chapter. So here on page 87, where they're talking about sum of squares block, sum of squares treatment, sum of squares block by treatment. That's an interaction, right? Looking at this formula, that's a formula for an interaction sum of squares as well. So that's an interaction sum of squares. When we come to the ANOVA table, they label it error and then interaction both. Excuse me. They label it error and interaction both to remind us, I guess, as far as what's going on there. But this interaction sum of squares is going to be the denominator for the main test about the treatments. Now there is one case that comes up further along in this chapter. Just to back up a little bit, they show you in the example that the F statistic for testing the treatment factor, mean square treatment divided by mean square blocked by treatment interaction. So there's the notation for the interaction. Notice it's the denominator. So that's the way the F statistic is calculated in the randomized complete block design. But further along in this chapter, on page a miscellaneous thought at the end of this chapter, right here, says use of more than one blocking variable. So in talking about blocks, we usually have some concept in mind about what our blocks are going to be. They might be plots of land. They might be cities, for example. And what this is suggesting is that sometimes your blocks are defined by more than one factor. And here's an example of the blocks. There's 4 blocks listed here, but the blocks are male, younger age, female, younger age, male, older age, female, older age. So the 4 blocks are defined by 2 factors, both gender and age. And that's okay. Nothing has inhibited us in talking about blocks along the way as far as how did we define the blocks. We're pretty much free and open to define them in whatever way we find helpful and useful. So here's an idea that maybe blocks are defined by more than one variable, and that's okay. Then, continuing on, this idea is good. Use of more than one replicate in each block. Let's see, there's probably a picture of an example coming up here. Yeah, this will work. So we have some kind of subjects. We have 2 treatments, low and high on distraction, whatever that means exactly. And then it says block is gender, male and female. So we have males here, and in this cell we have 4 males, not 1. In this block we have 4 males, not 1. In this block we have 4 females instead of 1. Here we have 4 females instead of 1. So notice how we have multiple observations in each cell. But this is still referred to as a block design. Okay. So this is opening up a small window that says, well, in block designs, you can't have more than one observation in each cell, as for example, data that might look like this. So how are we going to analyze data that looks like this? Well, we've got a few more options now with these extra observations. And if I just slide this a little bit further, they mention a model equation which has, let's see, how does this go? Overall mean, I think rho is the block effect, tau is the treatment effect, and then there's an interaction between those two, and then there's an error. So this equation, when you look at it as a model equation, should look to you just like a regular two-factor equation. One is blocks, the other is whatever our treatment is, and we have multiple observations in each cell, sort of like our original problem in whatever the first chapter was we were talking about here today, the two-factor ANOVA. It's exactly that model that you're staring at here. So what they're going to go on to do is to say, analyze this data, that kind of data there, just like you would a two-factor ANOVA, which are familiar to you. So we don't have to look at that any further. Let's see, there's something I'm looking for here. One of our handouts raised this issue. What about a data set where the sample sizes are, where the sample sizes are unequal? Our basic formulas were for the case where we had equal sample sizes in each cell. If they aren't equal, what do? Well, we raised the issue in a handout, and basically we said this is a messy problem and best left to our computer to do hard work for us. And so we did that with some examples. But what we recommended back in that handout is also being recommended here, in that when you have this kind of situation, switch over and use the regression approach to testing about the analysis of variance. So form the X matrix, form the beta vector of parameters, set up your reduced model, your full model, and do that kind of testing that you would do in a regression view. And that regression view doesn't have any restrictions about number of observations in each cell being the same or not. It just doesn't enter into the story, and so you can carry out the regression testing without worrying when you have unequal sample sizes per cell. So that's what they're going to emphasize here in the textbook, and it's a fine idea. I don't have any problems with it. Although it's kind of messy because you usually have to fit several reduced models. That's the end of that chapter. Chapter 24. Now, this is the one I'm going to recommend that you read and study. The title basically says what you're going to find here. It's going to talk about analysis of variance when we have three factors. So we did one factor in the beginning, then two factor, then we did block designs and stuff, and now here we've got 3 factors in the problem. So it's upping the game a little higher level of complexity in that sense. So what changes in our analysis of variance stuff when we have 3 factors? That's what you'll see in this chapter. So I'm not gonna go through this in class, you know, idea by idea and so forth, because I think the idea of what you do when you've got 3 factors is simple. You do the same thing that you did when you had 2 factors, just letting your mind expand a little bit to say, well, how do I have to, you know, add to the stuff to handle 3 factors? So that's what you'll see when you start to read this chapter, and I'm expecting you to find it fairly easy going. Okay. So there's hand calculations possible with 3 factors, but it gets to be rather oppressive because there's a lot of calculations to make with 3-factor ANOVA. So we can use our computer to produce standard output for us, and that's good. So we'll have a way to produce that as well. But just a few highlights here. Notice that the mu has 3 subscripts, I, J, and K. It's kind of buried in this paragraph right there, but it says mu I, J, K is the mean response. The factor A is at level I, factor B is at level J, the third factor C is at level K. So we call that mean mu I, J, K. So we've got 3 subscripts on any cell mean. We can't lay out these cell means on a 2-dimensional layout in front of our eye, right? It takes 3 dimensions to lay this out if we wanted to try that. I usually don't. So anyway, notice the dot notation is being used here. It's the same way we used the dot notation before. If you see a dot at the position of a subscript, that means we've added over that subscript. So mu I, J dot says hold I fixed, hold J fixed, and add over the third subscript, K. So where does he get into, here it is. The alternate model here, you will spot, and you will find it used quite often. This expression for the mu I, J, K should be mu I, J, K equals here. But it's an overall mean, factor A effect, factor B effect, factor C effect. There's an AB interaction. There's an AC interaction. There's a BC interaction. So if you've got 3 factors, you've got 3 different pairwise 2-way interactions. There, and there are the terms of the model. So there's still more going on yet. That's denoted by this symbol, alpha, beta, gamma, parenthesis, I, J, K. This is the 3-way interaction, or here, as the author calls it, the second order interaction. But I like to call it a 3-way interaction. So he's going to define with these equations, well, what is this 3-way interaction stuff you're talking about? Well, when he puts it all together, it's probably on the next page. There it is. He's finally looking at this model here, which has mu I, J, K. The mean, when A is at level I, B is at level J, C is at level K, is mu plus a rho effect, plus an A effect, plus a B effect, plus a C effect, an AB interaction, an AC interaction, a BC interaction, and finally an ABC triple interaction. These are the terms of the model. Now, this looks like it's quite complicated. There's a lot of stuff floating around in front of your eye. If you think about the pieces that are there, this should look really familiar. It shouldn't look that strange. Now, we have to worry about, well, how do we estimate all these parameters in the model? And so here they're expressing those parameters in terms of the means and sums of means, and then we're going to replace those means by sample means to estimate them. And so we'll have sample estimates of these parameters as this goes on. Then we will find there will be sums of squares corresponding to these parameters. So the story goes on. And here's the basic ANOVA table. We have sum of squares A, B, C, AB, AC, BC, ABC. And there's standard formulas for these sums of squares, which are in the text on another page. There's a sum of squares error. And so this is the standard ANOVA table for three-factor ANOVA. Standard degrees of freedom formulas. And here in this table, they did give us a column of expected mean squares. These are easy ones because remember, this is still a fixed effects model. A is a fixed factor, B is a fixed factor, C is a fixed factor in this discussion. So there's no tricks about random factors going on in this discussion. And so all these expected mean squares are basically a general error variance sigma squared plus a term that's referring to the variation in that individual factor. So this expression refers to A, this expression refers to B, this to C, this to the AB interaction, and so forth. These pieces all make some direct sense in terms of the effect that we're trying to talk about. So let me just quickly turn some pages here for my own view.
Excuse me.
Yes, Judith, you got a question?
Yes.
I'm sorry. When we have all pairwise interactions, doesn't it cover the interaction among the three?
Say that a little louder, Judy.
When we have all pairwise interactions, does it relate anyhow to the three interaction?
No.
No?
I'm not sure if there's a picture here that would address your question or not. Let me try to look at this picture for the moment. Here is AC graph. No. Excuse me. Factor down here is B. Factor labeling these axes is C. So this is a BC interaction plot when factor A is male. And then this is a BC interaction plot when factor A is female. So we have two graphs like this. Now, you see they're not the same. Okay. What that means is we have triple interaction in this data. If there's no triple interaction, these two plots should look identical. They're not identical, so we have some kind of three-way interaction in this data. And that's not connected with the fact that there's interaction between pairwise B and C, for example. It's just a new issue, three-way interaction.
So isn't an A and C interaction what we see at these plots?
Say that a little louder, Jenny.
Can't we conclude an AC interaction in these plots? Or only we can see is an A, B, C?
Well, I don't have an A in the plot. This is a BC plot, and that's a BC plot. So I don't have A in the plots. I'd have to redraw new pictures. And maybe put factor A down here on the bottom, for example, to see what happens. But I don't have A in either of these plots. If you like, A is separated out. This is one level of A, and that whole plot is for the other level of A. And that's all it does. Still, this is very handy to look at. If you wanted to say, what does three-way interaction look like in this example, you'd have to say, well, the pattern of the relationship between B and C that I see here, for example, and then as I see here, for example, the pattern of relationship between B and C changes as factor A changes. That's what three-way interaction is. Well, here's a different example. Now, he's put factor A here, factor B here, factor A there, factor B there, and then factor C breaks things apart into two pieces. So here's an AB interaction plot for one level of factor C. There's an AB interaction plot for the other level of factor C. And they're not too far apart, actually. They're pretty close, but I guess let me just say they're not the same. So there's some evidence of three-way interaction here, perhaps not as extreme in this data set as there was in that first data set that we were looking at. So things are more complex to talk about when you have three factors. You've got how does each factor work alone or by itself? You've got how do the two factors intersect with each other, A with B, A with C, B with C, and you've got all those choices. And so you need to say something about each of those issues. And then there's the issue of the triple interaction, which still needs to be discussed. If you have a data set which has triple interaction in it, I almost want to just throw it away because there's not much I can do to interpret a triple interaction. It's very complex. You can look at this graph at the top of this page yet again and see the complexity coming. If you had to tell somebody what this means, say it in words. Okay? Say it in words. What does this mean? That's not easy to do. I mean, it's not impossible, but it's fairly complex to do that. And so I cringe when I run across a data set which has some real three-way interaction in it because I don't know easy things to say about interpreting a three-way interaction. I'm okay with a two-way interaction. I kind of know what that means. A three-way interaction gets to be hard. Sure, they do lots of experiments with 4 factors. What if we had 5, 6, or 7 factors? They do lots of experiments with 7 factors in them. So if you've got 7 factors, think of all the two-way interactions that you've got to think about. It's a lot of them, right? Think about all the three-way interactions there would be. And if you've got 4 factors, you would have a 4-way interaction. If you've got 5 factors, you would have a 5-way interaction. And the game just sort of compounds up from this beginning start. So the chapter here in the textbook, which is talking about 3 factors, is good. It does a nice, careful job of the case of 3 factors. But realize as well that it's kind of opening the window to say, well, if I can do this sort of stuff with 3 factors, I can do the same kind of stuff if I've got 4 factors. And that's true. So then it's going to go on and talk about the analysis of variance, all the formulas for the sums of squares, the F-tests. Then it's going to talk about estimating the means, contrasts in the means, the usual kind of stuff that we did when we had two factors. I'm not going to dwell on this at all, but I just want to stop at this point here in the textbook today, because this was the last handout we had. Random effects. Well, we had one random effect handout. Then we had two random effects, and mixed model was the next handout. But anyway, that's here in the textbook. So this is going to talk about models which have one random factor, as we've already talked about. And it's going to talk about models which have two random factors, which we've already talked about. And it's going to talk about mixed models, where one of the factors is fixed and the other is random. So we've got those cases that are going to come up in this chapter. So anyway, I want to just lead you to this chapter and say, read it. This is good stuff to study. The formulas look fine. They should match the stuff that we talked about in class. And so it's a good background for these ideas of having random effects and mixed models as well. Things are going to get worse when we have four factors. We could have one fixed, three random. We could have two fixed and two random. We could have three fixed and one random. All those are possibilities. The formulas and the test statistics change in each of those circumstances. And we're going to have to try to figure out how can we identify the changes that come up when we have all these various possibilities. If you've got 10 factors, 5 of them are random, 5 of them are fixed, how are you going to construct the proper F-tests for testing various kinds of mean effects, various kinds of interactions, and so forth? What's going on? Well, we'll try to pursue those kind of thoughts as we go along further. But this is a good place for me to point you to say, read this textbook up through this particular chapter, and we'll be continuing on from this point after the break. Now, Johnson second run minitab. So I need to find Millikan-Johnson first run. So if I go back through my handouts that we did in class, let's see, it's probably in the handout about unequal sample sizes would be my guess. So I'm going to try that handout where it says unbalanced two-factor analysis of variance. And then there's a whole bunch of stuff pointing out that this is such a messy problem. And then, here on page 5 of 9, there's this data set. Okay, and it says Millikan and Johnson, page 128. And so there is the data. Now, this has 2 levels of factor A, 3 levels of factor B. So there's 6 cells here in this data set, and there's the sample sizes in the 6 cells. You see they're not all equal. So what did I do to get this output? I ran minitab with the command glm, and it produced this analysis of variance table. And then I ran SAS, And here's the SAS code starting at the bottom of the page. And it produced this stuff. Now, I apologize because I didn't check. Is the SAS output identical to the Minitab output, or is there a difference? So let me see how we can check this out. Let's try to look at C1 is A, C2 is B in this labeling here. I should have set the names of the columns better in Minitab, but I didn't. So C1 is A, and that's 61.7. Oh, one thing I forgot to mention. We talked about this when we have sum of squares called sequential sum of squares. We have the sum of squares called adjusted sums of squares, and they're not the same. So what kind of sum of squares are we going to talk about? So let's see, we have, for A, we have 76 and 61 for the two sums of squares there. If we look at the SAS output, it comes on the next page. What did I say? 76 and 61. Well, there's the 76 for factor A, and it's a type 1 sum of squares. Okay. Here's the 61 for factor A, and it's a type 3 sums of squares. So here's the labeled in SAS's language. Type 1 and type 3 sums of squares for this data are different, and there's the sums of squares. Now SAS kind of cheats on us because they do the full line. They give us a p-value, for example, at the end, right? So we can finish the test. How do we know which test to use? If I want to test about factor A effects, should I use type 1? Should I use type 3? In this example, both of the p-values are very, very small, so we would reach the same conclusion there. But that's not always going to be the case. I asked some other things out of SAS. So on page 7, I'm getting this kind of stuff, least squares, means. This kind of stuff here. Well, fine and dandy. So anyway, to come back to the example of the Minitab output, in Minitab I ran GLM. There's the response, there's A, B, and A, B interaction. So that's the model equation I use with GLM. Now in this new handout from today, it looks identical. Somehow I thought it was different, but it isn't. Oh, I see what I did different here. Here, this new handout today, see what I did. I set one of the factors to be random. And there it is right there, random factor B, which we didn't have in the Minitab one of the handout page. So there's the change, random B. Now, when we look at this data from Millikan and Johnson's book again, I don't have the background behind this example, so I can't say anything about it. Why would factor B be random? So I guess I'm just supposing that the context was such But factor A is fixed and factor B is random. And so this is what I specified in Minitab. So I get this coming out, and when I look at this, I have to say these numbers are different than the numbers that we had back in the course map page. Sequential sums of squares, 76 the same, 90 the same, 71 the same, 20 the same, and so forth. The adjusted sums of squares, the same. Adjusted mean squares, the same. F statistics, different. So there's where something changed because this factor B is now random. So we can look ahead and notice I had asked for the expected mean squares. So we have this layout in Minitab here showing us its calculation of expected mean squares. Oh, I'm sorry, I went here. So looking at these expected mean squares, we can find the proper denominators. For instance, if we want to test about factor A, we need to find something with this expected value, and it's not in the list. It's close, but it's not in the list. So let's say, suppose we want to test factor B. We have to find something with this as its expected value. And we've got one right there. So we'd say the test factor B is the AB interaction. Done. To test the interaction, we have to just use the error. 4 is there. So the error would be the proper denominator for testing interaction. The AB interaction is the proper denominator for testing factor B. But we don't have anything that's the proper denominator to test about factor A. So what does Minitab do? It does test about factor A. There's a row here, there's an X at the end of that row, which it says not an exact F test. Well, okay, whatever that means. I guess there's barely enough information in this Minitab output to see what they're trying to do. The Minitab was basically going to try to find a combination of other mean squares so that the expected value of this combination would be what it means right there. So it came up with this one right here. That constant times 3 plus that constant times 4. Well, 3 is the AB interaction and 4 is the error. So turn that constant times the AB interaction, that constant times the error, and then that becomes a new mean square. I guess this is one. So, is that in the table above? I didn't notice. So, So a mini-tab put an F statistic in row A and a p-value. And then X flagged it and said, hey, this isn't a real F-test. But anyway, it did that. So what was it doing to get this 1.73 for the F? Well, it has to be taking the ratio of two mean squares, right? So I think it's got to do. So it's got a mean square for A. Probably going to use the adjusted one, 61. And it needs a denominator. What's it going to use for the denominator? Well, it's going to use this thing right here, 35.64. I'm curious. Does it work? If I take the 61.714 and divide it by, just as a guess, that number, 35.64. I get 1.73. Yeah. So I didn't check this ahead of time. I was lucky because what if it hadn't worked and I'd be standing here stammering saying, well, now what should I say? Anyway, it worked. So anyway, you can see what Minitab is doing here. It's got a problem. It doesn't have the right denominator for A. So it creates one as a combination of two others. There it is shown. It's right there. Now, the problem is that's an F test, and there has to be 2 degrees of freedom connected with it, right? Well, there's a degree of freedom for the numerator. Factor A has 1 degree of freedom. What's the degrees of freedom for the denominator of that F? That's that thing there. So we have to have some way of estimating the degrees of freedom for this combined mean square here that we're using in the denominator. And that's possible. It's basically the same formula that we used when we talked about Welch t-test. Remember how we had to come up with an estimate for the appropriate degrees of freedom for the Welch t-test? It was kind of a messy formula that we had to work with. But anyway, it was there to plug in the numbers and calculate. There's a similar formula for this problem here, and it's in the textbook, so I can refer you there for more detail. But I guess what I'm trying to show you here is that in looking at this example, the Millikan-Johnson example data here again one more time, that things change depending on whether factor B is fixed or random. So in the course pack page, factor B, nothing was mentioned about it, so it's fixed. So both A and B are fixed in the course pack Minitab output. If we switch it, as this handout does, and make B random, then there's some changes that go on in the F test, especially for A. You know, there's more changes going on here yet. This is the new one from today. For testing B, the F statistic, which is a straight ratio, it's just 1.08. Go back to the class handout. The F test for B, which is the second one, F was 19.29. Way different from the 1.08 here. So there's something more going on in the difference here than just factor A. I don't need to talk about it here anymore today, but let's just leave that go. just notice that there's something different on factor B as well. Okay. All right, fast handout for 5 minutes. Yes. Is useful pseudo F test. So when we construct these F statistics with the linear combinations form, those are called pseudo F tests. So here's an example. The bottom of this first page describes the data set a little better about what are the different factors and so forth. But then the data appears at the top of the second page, where you see we have gate setting 3, we have operator ABC, ABC, we have day 1, day 2. And so we have 3 factors. Now it gives us this ANOVA table, which looks like something that might come out of ACAP. But I don't know what they used here for this source. But anyway, we looked at this column of expected mean squares here. By the way, I should say, first of all, look at all the cases that we have to test about. We have to test DO field interaction and G, and GD interaction, GO interaction, GOD triple interaction. So these are all the tests that are involved in a 3-factor problem. So here's the appropriate degrees of freedom, which you can track down appropriate with that data. But I want to know what are the possible F tests. So I'm looking at this and I'm saying day's got to be a random factor. These are just 2 days that sort of arbitrarily were picked to run the experiment. So those are random. So day is a random factor. Operator, as it said on the previous page, the operators were just selected from the pool of available operators, and so that would be treated as a random factor as well. So day is random, operator is random, but the gate setting is a fixed factor. So we have 3 factors. One of them is fixed, the other 2 are random. So that's what we have going on in this example. Now, if we just accept this expected mean square column here, notice that we're going to be okay in several of these situations. For instance, let's start at the bottom and work up. Do I have a proper denominator for this one? Yeah, here. Do I have a proper denominator for this one? Yes, the one just below it would work. Do I have a proper denominator for this one? Yes, the triple interaction again would work for that one. Do I have a proper denominator for this one? Factor G. Remember, G is the fixed one of the bunch. And I look at all the pieces that are here in the formula. I look at what's available to use, and I say, no, there isn't a single proper denominator to use for testing G. So pass that by, let's go up here to this one, the DO interaction. Looking at what's there, we would say, yes, use the error mean squares as a denominator, that would be fine. Coming to this one, operators O, is there a proper denominator for that test? Yes, the third one down would be right. And then going to the top one, days, Is there a proper denominator for testing days? And we can say yes. Again, the third one down has the right expected value. So I'm checking all this out, and I'm doing this kind of quickly here in front of your eye. You can see that there's a proper denominator for all the tests I want to run, except for testing G. So what am I going to do? Well, as it says down here, looking at what was left in this expected mean square, these are the things that I need. It said this can be found by the linear combination. Take mean square dg, mean square og, mean square dog, the minus, and then figure out the expected value of that by substituting in the individual expected values, and you get that, which is what we wanted. So here's our candidate for the denominator. So he said, well, this is going to be of this general form. The mean square is a linear combination of a bunch of other mean squares. And then it says the degrees of freedom for mean squares. This is approximate now. This is estimated. Sorry about that. And so here's the formula for estimating the degree of freedom. So plug in the numbers for this example, is what he does next. Here's plugging in the numbers. Calculate it out to be 4.2. So he says for this new constructed mean square, its appropriate degrees of freedom are approximated by 4.2. Now, what he says in the last line here is that he's going to use an F with 2 and 4 or 2 and 5 degrees of freedom. He'll split the difference, not really caring, because the conclusion is going to be the same whether he rounded this to 4 or rounded this to 5. It doesn't matter. So anyway, the purpose of this small example was to show you an example of some actually a very nice data set right there. And it shows you the expected mean square column, which was presumably done by Minitab. It shows that there's a problem with an F-test with G, and so he talks about how to construct this mean square, a linear combination of other mean squares, to do the job. So it's a nice short example to illustrate again what is called here a pseudo F-test. Okay, that's a good place to stop then for the day. So let me do that.